Hi, I'm Dr. Asegun Henry, and I'm a professor in mechanical engineering at MIT that specializes in heat transfer and energy systems. I want to use this opportunity to tell you about a technology that I invented that we've been developing in my lab called thermal energy grid storage using multi-junction photovoltaics, or the acronym TEGS-MPV. And it's also garnered the moniker Sun in a Box in some media articles. So our technology aims to solve the grid level storage problem so that we can achieve a fully decarbonized grid, which is arguably the single most important step that we have to take towards mitigating climate change. Now, the problem with renewables like solar and wind is that you only get electricity when the sun is out or when the wind is blowing. And without a way of storing the energy so we can use it later, we still have to rely on fossil fuels to balance out the demand for the grid. Now, the first thing you might be thinking is, well, why not just use lithium-ion batteries like electric cars? And the problem is simply that they are too expensive and they don't last long enough. Batteries today cost more than $100 a kilowatt hour, and they're slated in the future to maybe get down as low as $50 a kilowatt hour. But studies have predicted that in order to get to a fully renewable grid, we have to have storage below $10 a kilowatt hour. And lithium-ion batteries simply won't get us there. But our technology can. The way our concept works is that we don't store electricity electrochemically the way it's done in a battery. Instead, we store energy as heat. Now, if you've ever taken a course in thermodynamics, you would know that taking electricity, converting it to heat just so you can store it, and then converting it back to electricity sounds like a really stupid idea. And the reason it sounds stupid is because more than 90% of all electricity on Earth comes from heat to begin with. And when we convert heat to electricity, we pay a big thermodynamic penalty. And it's because we waste most of it. So we already waste a lot of heat making electricity the first time. So why would we ever make heat again only to pay a penalty, a huge penalty, to convert it back to electricity a second time? And the answer is cost. At the end of the day, cost is what matters. Automobile engines, for example, they're only about like 25% efficient. That means like 75% of the money that you spend to buy gas for your car just ends up wasted as heat going out the tailpipe. But we use these engines because they're cheap and because they give us the torque we need at low speeds to speed up really quickly after a red light. So the same is true for our technology. It's not as efficient as batteries, but they're about 10 times cheaper, and that's the key. Now, the way it works may sound like science fiction at first, but it's real. We've tested all the components separately, and they all work. Now we're building a fully integrated prototype in my lab, and once we show it all works together as predicted, we're looking to scale it up. So the way the technology works is that we take electricity from any source. It could be solar, wind, fossil, nuclear, whatever, and we then use that electricity to run resistance heaters that are basically the same as an incandescent light bulb, except instead of it being like a 100-watt light bulb, at scale this would be like a 100-megawatt light bulb. So it's like a million 100-watt light bulbs. These heating elements convert electricity to heat at nearly 100% efficiency, and they transfer heat to pipes made of graphite via the light that they give off. The pipes have liquid tin inside them, which we pump through to absorb the heat, which heats up the tin to a peak temperature of about 2400 degrees Celsius. Now that's glowing white hot. The tin is pumped then over to a big bank of graphite blocks that are at about 1900 degrees C. And the liquid tin heats the blocks up from 1900 degrees C all the way up to 2400 degrees C. And in this way, this big bank of blocks store the energy as heat. Then, when you want electricity, the liquid tin is pumped through the graphite blocks again. It heats up to 2400 C. It's heated by the blocks, and then it carries that heat over to the power conversion unit. Now, what's special about our technology is we don't try to do the conversion of heat to electricity the normal way, which is with a turbine. Instead, we use photovoltaics, since the entire infrastructure of pipes is glowing white hot. Instead of spinning a super hot turbine at 3600 RPM, we instead just convert the light coming off the piping using the PV cells. Now, these PV cells are not your normal PV cells. All right, these cells have mirrors on the back because we don't even try to convert most of the light. We actually only try to convert the highest frequency light, which we can convert most efficiently. The rest of the light we can't convert efficiently, so it actually bounces off the mirror and goes back to the hot piping, where it gets reabsorbed and it's preserved within the system. And what I mean by that is we actually reflect the light so that we can save it. And this is where this name, this moniker Sun in a Box, came from, because our system is glowing white hot like the sun, but we've trapped it inside a box where it can't get out. And this makes our system efficient, where our target round trip efficiency, which is the fraction of electricity that comes out divided by what came in, we're targeting about 50%. Now, the other interesting and special feature of this technology is that the cells can actually be actuated in and out of the light. Even though the piping is extremely hot, the cells remain cool near room temperature because they're mounted to a heat sink that's water cooled. This heat sink can then be actuated into and out of the light on the order of seconds. So this means our technology can ramp from fully off to fully on within seconds, which is something that it takes turbines like tens of minutes to do. And it shortens their life as well. Now, the reason this is important is because it means that our technology can actually provide greater stability for a fully renewable grid by compensating for small fluctuations in the output that change with the transient weather. Now, what's critical to understand about our technology is that the entire system is held inside an inert environment. So there's no oxygen. Almost the entire system is made out of graphite, which is cheap. And the amazing thing about liquid metal, tin, and carbon is that they don't exhibit any chemical interaction at any temperature. This means there's no corrosion in our system whatsoever, not at any time scale. So for this reason, our system should last well beyond 30 years. So there's no real degradation mechanism. Now, the other key thing that may seem like science fiction is the fact that our system relies on pumping liquid metal tin at seemingly unimaginable temperatures. But what prompted us to develop this energy storage idea was the fact that we demonstrated a key technological breakthrough a few years ago, where we showed we could make an all-ceramic or all-graphite pump for liquid metal. In the initial demonstration, we pumped liquid tin at 1400 degrees C, and we set the Guinness Book World Record. But since then, we've actually pumped liquid metal above 2000 C. So we've even though it may sound insane, it actually works. Now, the most important selling point of our technology is its cost. As I mentioned before, lithium-ion batteries cost more than $100 a kilowatt hour, but we're much cheaper than that. And the way you can see this is to look at the cost of the main thing we're storing, which are these big graphite blocks. Those blocks cost about 50 cents a kilogram. So if you divide that 50 cents a kilogram by the heat capacity and the temperature difference, which is about 500 degrees C, where we go from 2400 C down to 1900 C, then you have to also multiply by the efficiency, so you get that graphite costs about 1/millionth of a dollar per joule. So that's like $3.6 per kilowatt hour. Now, this is just the starting cost. But even after you add on all these other components, the construction cost, the insulation, etc., it still comes out below $10 a kilowatt hour. Now, the second bar on the right shows the cost breakdown for all the components that scale with the power of the system. So these costs are about half that of a turbine. So by using the PV cells to do the conversion, we get turbine-like efficiency at about half the cost and with much faster response. So we're working hard now to demonstrate this technology in my lab to make a fully functioning prototype, and soon we'll be looking to gather partners and build a 1 megawatt hour pilot. We've demonstrated the pumping, the materials, the seals, the heaters, and most recently we even demonstrated the PV cells at about 40% efficiency. So we have all the pieces ready, and if you're interested in supporting our research to help make Sun in a Box a reality, please do not hesitate to reach out. Just Google my name, Asegun, and you'll find me online.